Hello and welcome to another exciting edition of the TreeStuff educational webinar. Thank you for being here. I'm Jake Miller. We are back after taking a break to host an incredible Jambo 6, and we are here tonight to bring you a very special webinar, Electrical Hazards in Tree Care with Keith Blakeslee. Now, Keith is going to discuss the OSHA guideline and provide a base knowledge around what electricity is, how it works, and how it could affect you out in the field. Keith's also going to be answering your questions throughout the webinar. And as always, we'll be offering 2 ISA CEUs through a quiz after the webinar is completed. So let me now send it over to Keith Blakeslee. And Keith, thank you so much for being here. We look forward to hearing what you have to say tonight.
Okay, all right. So Keith Blakeslee with the Northwest Line Joint Apprenticeship Training Committee here out of Washington. Excited to be here with you guys. Thank you, TreeStuff, for the opportunity. So sit with me here on this slide as we go through this PowerPoint on electrical hazards and awareness for the line clearance tree trimmer and the general private arborist. We doing good? So the Northwest Line JATC, we are a training entity sponsored by the International Brotherhood of Electrical Workers and the National Electrical Contractors Association. We train in the industries of outside power line construction and line clearance tree trimming through registered apprenticeship programs. We've been doing this since 1985. We are a very, very unique company. So we handle areas of Washington, Oregon, Northern California, and Northwest Idaho. And then IBEW Detroit 17 also has a similar program to ours. So not only do we have apprenticeship programs, but we also have pre-apprenticeship programs. And the pre-apprenticeships are designed for anyone who's wanting to get into the electrical industry or the line clearance industry and maybe just doesn't have a good background or they need more experience. So Volta Vocational Outside Line Training Academy and Volta Tree are 2 programs that we offer here in Washington and Oregon State that help anyone, again, wanting to beef up their resume and get some solid experience before they go out and try and apply in the industry. So again, following lineman and tree trimmer, these are our 2 main focuses that we teach on here at the Northwest Line JATC. We do have some really, really good program sponsors like Buckingham and Rock Exotica, and DMM, and Samson, Petzl, companies that do supply us with some good equipment and help our training be as best as it can be. A little introduction about myself. So again, my name's Keith. I am a journeyman line clearance tree trimmer. I realize that for some people in parts of the country, they may not know what that is. I went through a registered 2-year-long apprenticeship program and then took a journeyman exam through the International Brotherhood of Electrical Workers, obtaining my journeyman license. I'm an instructor for the Northwest JATC. I'm also an OSHA outreach instructor. I develop curriculum for our Volta students, and I've been in the electrical industry for about 14 years. So the agenda that we're going to go through today is the introduction that we just got done doing. We're going to look at some regulatory references, definitions, and terms to make sure that we're all talking the same language, so I'm not saying things that maybe you're not familiar with. We'll look at some overhead and underground equipment identification, electrical faults, direct and indirect contact, equipment and electricity, power lines under tension, grounds, and personal protective equipment. A quick disclaimer that I have to go through with you guys. So no act or technique discussed or taught during this presentation is to be done without proper training, licensing, certifications, and supervision. Working around electricity or within MAD as a tree trimmer shall only be done so by documented line clearance certified workers or trainees. If you guys would like to follow along on a lot of these slides, I do have direct page numbers cited. So if you guys have your OSHA or your Z books here with you, then you can bookmark them or tab them out so you can find items later. But it's the OSHA 1910, OSHA 1926, and ANSI Z133 are the regulatory references that we'll be citing out of today. Getting into it, so electrical hazard awareness program. This presentation here is to give you guys an idea of not only what we do, but also to ensure that you guys out there in the field as power line clearance tree trimmers or general arborists, you guys can have a little bit of knowledge in your back pocket as far as what electricity is, how it works, where it comes from, and just some general safety precautions to ensure that you guys aren't exposed to any risks. And we're going through this program today because we all want to make it home in the same way we came to work. We all have families that we make money for, that we provide for. We want to watch our kids grow up and succeed in life. You know, we do a dangerous job to succeed, to make money, to experience things, to purchase things, to grow old together. And it is a dangerous job. I'm aware of that. So we're going to talk about, you know, again, hazards that we can make sure that we try to avoid. We've all seen on Dripline or on Facebook or other social media websites, we've seen where people are hurt, where injuries happen. And this is the most recent statistic I could find on the Dripline. So this was for August 2019. So we've had 68 total fatalities. And out of that, that's 20 tree care professionals and 26 civilians. So those numbers are too high. So hopefully throughout this presentation, we can make sure that you know, we are each other's brother's keeper, and we can keep each other out of harm's way. According to OSHA, almost 60% of industrial deaths were in one of the big four categories. And the big four categories: falls, caught in betweens, struck-bys, and electrocutions. According to OSHA, in the year 2017, there were 71 deaths by electrocution. So our objectives getting through this is we're going to talk about identifying what is hot and what is not. So what is energized and what is not energized. Ways to avoid electrocution, common hazards, step and touch potential, hardware recognition, electrical PPE, and qualified versus non-qualified. As we get started, we need to be able to speak the same language like I mentioned earlier, because just like this slide here, if I tell you to let it run and I'm up in the hooks and you guys cleat it off on the porter wrap and I go for a ride, you know, so basically we need to speak the same language. So where does power come from, right? So we see on this slide that we can have solar, nuclear, wind, or hydro. Those are the four most common forms of electrical generation, hydro being definitely the biggest. And it's transmitted over high voltage transmission lines, and then it comes down into a substation to a lesser voltage, and it's transmitted again on subtransmission lines, then to distribution lines, then to a single phase, finally getting to the house or the business. This is a great little depiction. So this is amps, ohms, and volts. And what we see is we have an amp in an orange shirt trying to squeeze through a pipe, and the ohm in the green shirt up top is squeezing that pipe. That ohm represents the resistance. The pipe is obviously the flow of power. It's the power line itself. And then we have a volt. And what happens in power lines, you know, or during fault situations or in heavy load times, the larger the amp is, the harder it is for that amp to get through the conductor. So if the voltage is bigger, he can get a larger amp through the conductor, or if there's less resistance. So the higher the voltage, the easier it is for the volt to push the amp. The higher the resistance, the harder it is for the volt to push the amp. The bigger the amperage, the harder it is to fit through the resistive conductor. So some of the terms that we're going to go through and look at definitions are dielectric, neutral, ground, circuit, phase, insulator, upstream and downstream, backfeed, protection device, and qualified. Qualified line clearance arborists. Now these are direct quotes from ANSI and OSHA. So an individual who through related training and on-the-job experience is familiar with the equipment and hazards in line clearance and has demonstrated the ability to perform the special techniques involved and who is working on behalf of the system owner or operator. And OSHA, an employee or person knowledgeable in the construction and operation of the electric power generation, transmission, and distribution equipment involved, along with the associated hazards. This is important for me to let you guys know. OSHA 1910-269 clearly states what a certified line clearance tree trimmer is, and I just want to make sure that as we go through this presentation and we talk about tools or techniques or ways to do a certain job, I want to make sure that you guys realize that there's a lot more training that's involved, and this PowerPoint presentation is not meant to be all-inclusive. So an example of what qualified versus non-qualified looks like, we have a power pole here, and within that 10-foot mark, me, a qualified line clearance tree trimmer, I can work within that 10-foot mark up to MAD, or a minimum approach distance. If you are a non-qualified line clearance tree worker, or just a non-qualified person in general, OSHA and ANSI dictate that you must maintain at a minimum of 10 feet away. Dielectric, so this is a common used term as dielectrically tested, ensures that whichever tool, device, or apparatus has undergone high pot or high potential testing to ensure that that specific device will not conduct any electric current. I know Nick in an earlier video did a great presentation on hard hats and what dielectric means and how they go through the process of high pot testing. Hard hats, it's a similar process with lineman insulated gloves or dielectrically insulated tools. Some examples of dielectrically insulated tools is a switch stick, an insulated pole pruner, lineman hot gloves, some aerial lifts, and E-rated hard hats. Backfeed is a dangerous one and something that's very serious that every arborist or lineman or anyone working around power lines should absolutely be aware of. Backfeed is very common during storm situations where there's a power outage and a customer has installed a generator and they have either installed it incorrectly or they have failed to isolate themselves from the electrical system, and their power that they're creating from their generator can backfeed through the electrical system out onto the actual distribution wires and potentially injure a tree trimmer or a lineman that's working out there on the wires. An example of upstream and downstream and backfeed here. So if I was to describe backfeed or where I was at a physical location on power lines, right? So I'm standing in this mid-span, and anything upstream from where I'm standing would be considered towards the source or the generation or the breaker, and then anything downstream would be considered the load or the homeowner, the house, or the business. So upstream and downstream is common words used in my industry where we can explain to someone where we're at in relation to the power lines. Protection devices. Protection devices, when a fault condition happens, the electrical system has components and hardware in place to limit the fault duration and magnitude. Any device installed on an electrical system to aid in the automatic coordination of isolating a fault could be called a protection device. So think of a protection device as a 12-volt fuse in your car or the breaker in your house. When those apparatuses experience over amperage, or they experience a situation that is over their rating, right? The fuse, the element in the fuse itself melts and creates an air gap so no more electrical current can pass. Same thing with your breaker. So when you see a fuse out on a telephone pole or power pole, just think of that as a protection device, and if it experiences an over amperage situation, it can, it'll blow and create an air gap so power can no longer flow. Conductors, there's many conductors out there. Conductors can be anything from copper wiring, a cyclone fence, trees are conductors, humans are conductors. So make sure that if there's a situation where down power lines exist, you're not anywhere near any conductors. The next slide is a video of a cyclone fence where a power line has fallen onto it, and you can see how much you can see the fence essentially catching on fire and the ground catching on fire. It's just amazing what power can do. So that was conductors. So moving on to insulators. Insulators, we use insulators all the time. So there's glass insulators, porcelain insulators, rubber insulators. On the slide, there's an orange insulating sleeve, which linemen will install to protect themselves, or sometimes they'll install them for line clearance tree trimmers if the power lines are very, very close to the work that they need to be done. Reclosers. Reclosers, they can either be 3 phases or they can be individual, one for each phase. And the one on the slide here is a 3-phase recloser. And reclosers are a device, if a fault downstream happens, the recloser will open up, isolate in that area, and then reclose on that area to re-energize it. These things are particularly dangerous. You want to make sure that if you are working downstream of any reclosers, you are absolutely aware of it. So for the line clearance tree trimmers out there, be aware of what these look like on your particular system or your utility's particular system, so you're aware of it. Because in the next video here, we're going to watch a tree fall through the lines, and you can see it arcing, and then it stops, and then a recloser closes back in. So just imagine if you were to run up after you thought the power was out, and then it could close back in. So you need to be absolutely aware of it.
Fuck.
So just because you think the power is off, that doesn't necessarily mean that the power is actually off. Regulators, these are large devices that can either be found on regulator racks in stacks of 3 or individually on poles. They're essentially large transformers, and they are adjustable, usually manually adjustable, and you can find them in areas far away from the substation where there's voltage issues or concerns of poor voltage. Capacitors, these are not circuit protection devices. These are kind of like batteries. So they actually store electrical energy and help provide capacitance to the electrical lines. These things, the only way they can be considered safe is if they were shunted or shorted out. So if you are working downstream of these and you think that you're safe or that there may not be any power, be sure to again look for any capacitors, because if you think the power is out, these capacitors could be releasing a slow charge into the line. Looking at transformers. So transformers range in all sizes. They can be as small as 7.2 kV or less, all the way up to 500 kV or more. And that's, when I say kV, that's 1,000 volts. So 7,000 volts, which is a really common distribution voltage, or up to 500,000 volts, which is quite intense. The system neutral, so depending upon where you're at in the country, they might put the neutral at different heights along the pole. This construction here in the picture is very common to the Northwest. So the neutral is an electrical conductor that provides a path for any unbalanced load back into the system. So a really, really common misconception is that the neutral actually doesn't carry voltage, it doesn't carry any amperage, and it cannot hurt you. And that is simply not the case. The neutral has absolutely every potential to kill you. We saw an image of a fuse earlier at the circuit protection devices, but this is a little bit more detail. So the utility cutout acts much like a 12-volt fuse in your car. It's rated for a certain amperage, and when it experiences a higher load, the element melts. When a utility line experiences a higher load than its rated capacity, the fuse, or protective device, melts and blows apart, isolating the higher load downstream. And the reason why it actually blows apart, think about it like this. If you've ever changed a light bulb, and because the filament burned out, and you went to unscrew it to install a new one, and those filaments happen to touch each other and that light bulb lights up for just a second, that's what we absolutely want to prevent out on the line. If that cutout blew for a particular reason, then we don't want to inadvertently let those contacts touch again, sending power to a fault or to something going wrong on down the line. So that is why they're so loud when they do explode, because they are actually physically blowing apart. Electrical potential, so what we hear is that we have a copper atom. It's the ability from one charged object to send electrons to another object of different charge. So potential is measured is a measurement of electrostatic force. If two metallic objects of different charge are within arcing distance of each other, they will naturally try to balance one another with a positively charged object, pushing electrons toward the lesser attracting electrons from the positively charged atom, much like magnets. I know that was a lot, guys. Stick with me here, though. Electrical arcs. So this is a pretty good little depiction given to us by Creative Safety Supply. So an electrical arc is the visual and audible display of electrical transfer. Electrical arcs are a common sign during storms when tree branches are coming into contact with electrical lines, creating a fault. To put that into perspective, that big blue ball of fire that you see when things are going wrong on overhead electrical lines, electrical arcs can reach up to 35,000 degrees. That's quite hot because it's said that the surface of the sun is 9,000 degrees and human bodies are cremated at 1,800 degrees. So 35,000 degrees is quite hot and can prove quite disastrous to the human body. Clearances are quite important. So a clearance, it's sometimes called blocking, depending upon where you're at in the country. But a clearance is a term used within the utility and line clearance industry, whereas a lineman verifies a section of line is de-energized and isolated. Once the section of line is de-energized and isolated, the lineman will request a clearance on that particular section of line. They'll test it to make sure that there's no voltage in that line, and then they'll ground it at the immediate work zone. And the grounds, these grounds, in the event current was to inadvertently flow, provide a quick and easy path to ground, a quick and easy path to ground to trip the circuit upstream or direct the current to ground and away from the workers. So the grounds, which we'll show a picture here in a minute, the grounds actually provide a very, very clean and quick path to ground, essentially creating a short on purpose to make sure that any upstream protection devices actually will operate and blow, keeping the power out of that area. Personal protective grounds or equal potential zone grounding. So during both routine work and storm work, you will see grounds hanging from all of the phase wires, the neutral, and the pole ground. These grounds create a zone of equal potential, safe for the lineman to work in. If a backfeed or a fault was to occur, the grounds provide the shortest and quickest path for the fault to travel to ground, while also providing an opportunity for an upstream protection device to operate. Electrical lines should always be considered energized until they have been verified dead and grounded. So whether you're a line clearance tree trimmer or a general arborist or just trying to help out in the event of a storm, always consider power lines energized with potentially fatal voltages until they have been isolated and grounded and verified that they're dead. So here's a picture of some grounds and a lineman installing grounds. So you can see below his feet he has a grounding bracket attached to the pole and some hot wire gauge cables going to each of the 3 energized phases and the neutral, giving him a nice little safe area of an equal potential zone where he can safely do his working without fear of being electrocuted. Something that every line clearance tree trimmer or person working around energized power lines should absolutely be very aware of is ANSI's MAD chart. So this is the minimum approach distance. ANSI has provided 2 approach distance charts that shall be followed by everyone. One chart is for qualified individuals, while the other is for non-qualified. So we talked about qualified versus non-qualified earlier. We each have our own chart. The distances listed correspond to its partner in voltage. The higher the voltage, the further you must stay away from it. So as we click through the minimum approach distance chart, we'll see some areas light up. And so on the left column, we have, it's for arborists that are non-qualified. And if you look at 50 kV or less, you have to maintain a minimum of 10 feet away. And that's the lowest voltage that they have listed. So no matter what, you're going to stay at least 10 feet away. And then if you look on the chart on the right, which is for qualified arborists, if you look at the 50 kV zone, which is 46.1 to 72.5, the minimum approach distance for a qualified person is 3 foot 6 inches. So you can see that there's dramatic difference there between someone qualified and non-qualified. And then as we continue on the chart, you can see that as sea level, as we get further away from sea level and our elevation goes up, that the minimum approach distance also goes up because the air is thinner or there could be more moisture in the air, making it easier for electricity to arc. So now that we're kind of talking the same language, let's look at some overhead and underground distribution setups. And just as a reminder, electrical utility construction is not standardized across the country. So the following examples and images of common types of construction, but they do not include all types of construction. So on this slide here, as we click through, we'll begin to look at some different parts of single-phase construction. So starting at the top, we have one conductor. It's a single-phase conductor, and it's attached to an insulator, and that particular insulator is a pin-style vice-top insulator. So in the olden days, the conductor would actually lay in a kind of like a trough or dip in the top of the insulator, and then they would wrap it to the insulator. Well, nowadays there's a lot of these styles becoming more prevalent, and these are actually vice tops. So the wire will lay in the trough, and then the lineman will use their insulated tools and screw that vice shut, so it actually pinches the wire in place. And then moving down, we have an expulsion cutout and surge arrestor, and again, moving further down, we have the transformer, and you can see the low voltage service cables come out of the transformer. Those three cables, when they're arranged in that fashion, are commonly called a pitchfork. And then even lower, we have the crimp connector on a service drop or a triplex. Single-phase construction is what you will find on residential streets or other areas with minimal industrial load requirements. Their voltage varies from area to area, but is typically around 7,000 volts. Moving on to the next slide here, this is a common three-phase overbuild with an underbuild. So when there is conductors that have other conductors built below them, generally overbuild and underbuild is a common term used to signify which is which. Three-phase construction begins at the circuit substation with three individual phases running parallel. Common in both busy areas with businesses and rural industrial facilities. Three-phase distribution can be as low as 12.5 kV or as high as 27 kV, and in some areas it's even higher. So again, starting at the top of the pole and moving down, we have pin-style ceramic insulators. There is these phases on this particular construction is set up with a dead-end insulator with a jumper wire going from either side of the cross arm connecting it. And the conductor is energized ACSR, which is aluminum conductor, steel reinforced. And then on the secondary cross arm below, we have a lightning arrestor and fuse combo and single phase transformers. Going to the left is an overhead service triplex. And on the right, we have a guide line and underground services. So running vertically up the wooden pole is a piece of PVC or Schedule 40 PVC. And sometimes it's called a dip, an underground dip. And that is, in this depiction, being used to provide underground service. Excuse me, one moment. And on the next photo, This is three-phase overhead feeding and underground circuit. So again, you can see schedule 40 going up the pole, and you can see coming from the cross arms on each phase, there's what looks like a little gray insulator, and those are commonly those are underground cable terminations, or commonly referred to as potheads. And so this is actually, versus the last photo, it was a secondary voltage. It was a lower service voltage going to the house. In this situation, this is actually distribution voltage going to maybe a business. It's a higher voltage. These on this next slide are quite common. These would be referred to as open secondaries. So, excuse me. Open secondaries are not as common as they used to be. It's an older type of construction, and these are actually bare energized wires that are arranged very close to one another. The benefit to these is that the lineman could install a service drop anywhere within the span on these open secondaries because they were bare conductors. But in the event of a storm or even a balloon floating away out of the child's hand, these conductors are so close together that they can cross phase very, very quickly, very easily. So that was some overhead construction, and electricity isn't just transmitted overhead. It's also transmitted underground. There's estimated millions of miles of electrical conductors buried underground, some of which we don't even know are there. And since we don't see it, we don't necessarily think that it's actually a hazard. And it's very, very important for everyone to be aware of the different components that are installed, or just at least identify that there might be something there underground before you go ahead and aerate or inject some type of fertilizer in the soil, or before you start stump grinding, or possibly if you're not using zero impact methods to chunk down a tree and you're just throwing chunks off the tree onto the ground, it's important to know what's below ground level, right? So these here, these big green boxes, right, we've all seen them. Very, very common that homeowners will plant trees or shrubs around these underground vaults, and they'll have their tree maintenance guy or their landscaper or what have you come and maybe maintain these things or remove them once they get too big, or the utility will hire somebody to come out. And what will happen is the tree's roots a lot of times will infiltrate these green boxes growing in between conductive parts, and you go in there to start to remove them, and you might be in there with a handsaw and trying to cut a root out or cut a branch out, and it's sitting there moving back and forth inside the electrical box and can make contact in there, causing a fault. So these things are absolutely very dangerous, and these only line clearance tree trimmers should be working around these things, or if the utility is there with you and has told you that it's safe. To give you guys an idea, this is a lineman, and he is standing at a far distance from one of these boxes with an insulated tool, and he has a hard hat on, his safety glasses, fully insulated gloves, and insulated sleeves. So this is what the qualified guy is doing here to work around one of these things. And if you're not using these tools and you don't know what you're doing, then please, let's just not try and open these up or remove any branches or debris around them. Because on the inside of these things, as you can see in this picture, so these are distribution cables that are ran inside of plastic PVC piping. Once they've reached their location, they're ported up through the pad mount and into the device's cabinet. And each one of these cable terms, these are all conductive elbows or conductive components inside these green boxes. And the photo on the right, that's all Schedule 40 PVC with electric cables installed in them. So you can imagine all new construction or housing developments or businesses, there's a lot of things going on underground. These photos are pretty great. So you can see it looks like a mountain ash tree that's been planted right next to a pad mounted transformer, and then we have another one, it looks like maybe ants or dirt of some kind has infiltrated it. So just working around these things and bumping them, or again knocking around tree branches or roots inside of these things, can just be enough to set it off. And when these things do have a fault on the inside, they can be absolutely catastrophic. So this one here is a switch cabinet or a transformer cabinet that actually caught on fire and blew up. So you can see the entire structure is completely warped and concaved and just absolutely destroyed. You would not want to be anywhere near one of these devices when an internal fault occurs. So we kind of know that there's power lines laid underground, right? And something to be aware of as a line clearance tree trimmer, or if you are going to go do some stump grinding, is that the APWA uniform color code, specifically the color red at least, is electrical. So if you are digging and you come across red slurry or red concrete or red tape buried in the ground, usually that denotes that there is electricity below that tape. So if you guys are going to do any type of digging or tree transplanting, or again doing soil injection, fertilizers, stump grinding, absolutely do 811, dial a dig, and make sure that there is nothing below the surface that you're going to run into. And if you guys are installing or planting trees for your customers, and they have a pad mounted transformer on their property, 6 to 10 feet all around that thing is kind of a general accepted clearance. So just be sure to explain to them, hey, I can't plant this any closer than 6 to 10 feet. That gives enough room for the lineman to get in there and get the doors open and make any adjustments that they need to, or make any repairs. And let's see here. Looks like we're moving ahead. So hold on one second here. Anyways, it's very important to be aware of what's underground. So if you're sending wood and you're not using zero impact methods, you want to make sure that there's nothing underground. So how do you make sure there's nothing underground? You do the dial a dig, 811, and let's see. Can we? We'll go to the next slide here. See where we're at. All right, there we are. So I'm looking at this slide. You can see in the bottom left of that slide, you see 4 objects there on the ground, right? You see maybe a small power pole and some green boxes, but what you don't see is the intensity of stuff that is actually going on beneath the surface. So we've got some red color, some orange, yellow, and green. So we've got water lines, power lines, gas lines, and communication lines all within these people's front yard. So if you see boxes like this, or if you see a water meter, or the green pad mounted transformers, just know that there's something going on underground that you don't want to potentially entangle yourself with. So again, you have the dial a dig option, and then doing a quality job briefing is another lifesaver. So when you guys do your job briefing, make sure that you have everyone that's part of your crew there, everyone participating. You guys are all communicating amongst each other. 4 eyes, 2 eyes, 3 eyes. The most amount of people looking at a particular property than just one person is good, because we all know that somebody else might see something that I didn't myself see. And during the job briefing, if you guys are aware, or if you see things, if you see sprinkler heads or water meters or what have you, identify them, put a cone on them, or cordon them off, put a piece of plywood over them, do something to protect them, because you don't want to be the guy that is left there late at night at a job site, fixing a customer's sprinkler or whatever the case is. And if you're breaking water lines and electrical lines can get pretty high in cost to replace if you end up breaking them. The job briefing there on the left, that's a pretty in-depth job briefing. I know that OSHA has some examples of what job briefing should look like or what they should include. So if you guys aren't doing a quality job briefing, I think it's absolutely imperative that you do include and do a good job briefing as a crew. Moving on to faults. So we're going to talk about two different types of faults. Basically, we're gonna kind of categorize them into phase-to-phase faults and phase-to-ground faults. And a fault occurs when there's an unintended path to ground. Faults are commonly separated into two categories: phase-to-ground or phase-to-phase. And these are the #1 catalysts to overhead line faults. So branches break off in a storm and land on multiple phases, or a tree falls and tears down a section of wire with it. So we've all seen as line clearance tree trimmers or arborists where during storm situations where tree branches break off, land on the power lines, and the power goes out and creates what we see here. This is a fault. So there's actually an electrical transfer between the branch itself going from one conductor to another conductor. So that's a tree branch. And why are trees so conductive, right? So according to the U.S. Geological Survey, a mature oak can transpire upwards of 40,000 gallons of water per year. That is at 109 gallons of water per day. So at any one given time, you can expect a healthy large tree to have quite a bit of moisture in it. So through transpiration, the tree is full of wire, right? And obviously it's connected to the ground. So if power lines are nearby, close enough to arc, you have a very, very conductive object providing an excellent path to ground. So it's kind of a simplified, example, but that's the basis of it. So getting in again to the two different types of faults. So we have a phase-to-phase fault. So this is where a branch has contacted multiple phases at one time. So it's not just a branch touching one wire like a bird would be. So if a bird, we've all seen a bird land on a wire and nothing happens to them. It's when they touch more than one, or they touch one and ground, or something else where power can flow through them, becoming part of the circuit. So again, this is a phase-to-phase fault. So the branch is falling onto the power lines below, touching multiple phases at the same time. The branch has enough moisture to conduct electricity. Whatever difference exists between the lines will travel through the branch, causing a short circuit or a fault. If a fault is left unchecked and fed from the power system, the wires could eventually burn themselves to the ground. So we talked about circuit protection devices earlier, like a fuse. If there was a fuse that did not see this fault, right, then the generation and the substation would continuously pump power to this fault, and which could eventually lead to the power lines actually burning themselves in half. And then what you have, live electrical conductors contact to the ground, which is an absolutely very, very dangerous situation. And on the next slide, we have a phase to ground fault. So we've got power lines on either side of a tree that unfortunately decided to fall over or was felled and tore down the power lines. And we can see on the right that the power lines are contacting the ground. So this is a phase to ground fault. The fuses on the right opened up when the phase to ground fault occurred, and once the fuses blew, there's obviously no power going downstream. So the ones on the left are out of power. So we know why trees are conductive. So why are people conductive, right? So even ANSI knows that people are conductive. ANSI says the human body is conductive and poses little resistance to electric current and will provide a path for electricity to a grounded object or to the ground itself. So we can see that in this little blue color in here that humans have about 70% of water in them. I've heard that number vary before. Either way, it's quite a bit of water. And an ATC statistic, arc flashes cause on average 2,000 burn injuries per year. So that's a lot of burn injuries. So we don't want to be one of those statistics. So we know what there is phase-to-phase faults and phase-to-ground faults. And what we're going to look at here now is what happens when, how that fault occurs when we as people get involved with electricity. So remember that it only takes 1/10 of an amp to kill a person. And there used to be this common misnomer that linemen or electricians, if they wanted to test to see if a line was hot, they would touch it with the back of their hand, because if they gripped the wire or touched it like this and 1/10 of a milliamp went through them, that's just enough to cause muscle contractions, so they would actually grip onto the wire and would not be able to let go, leading to electrocution. So either way, we're not going to grab it and we're not going to touch it with the back of our hand, okay? Because it only takes 1/10 of an amp to kill a person. So in this slide, we have a power line, and we've got what looks to be a hemlock tree and a climber going up. And this hemlock tree is very, very close to the power lines. If the person, the worker, was to touch the power line while he's providing a path to ground, that would be direct contact, and that would be a phase to ground fault, and he would most likely be dead. Now, it's considered direct contact because he is literally touching it. There's no other medium between the person and the electrical conductor. And again, he is providing an excellent path to ground. On the next slide, we have indirect contact, right? So this is indirect contact. So there's another medium between the person and the electrical conductor. So this is kind of the easiest way that I could show it to you guys here. Is we've got a gentleman, and he's got a branch in his hands, and he's holding the branch, and he contacts the power lines with it. So that would be an example of indirect contact, and it's a phase to ground fault. So the power is flowing from the energized phases through the branch into the person down to ground. So it's phase to ground, and it's indirect. And the last one we're going to talk about is a phase to phase. So we have a climber here who, again, is working really, really close to the power lines, and he got carried away, and he kicked away from the tree to rappel. And he rappelled and landed on all 3 phases of the electrical lines. This is a phase-to-phase direct contact. So he landed directly on the energized power lines, and he's contacted more than one energized phase at a time. So it's a phase-to-phase. And just to keep in mind, too, that you don't have to lay on the power lines to be electrocuted. If the climber is contacting the tree by either hand, foot, or spur and touches a phase wire at the same time, this could also result in a phase to ground fault. And we've talked about the 2 different kinds of contact, electrical contact, direct and indirect. But before we take a break here, this is, contact is contact, and that's just kind of going to be my last little thought before the break. It doesn't matter if it's indirect or if it's direct. It's still contact, and becoming any part of the electrical circuit has the potential to kill you. Yep.
How about now? Can you hear me now? All right, well, we hope you're enjoying the webinar right now. We're going to take a little bit of an intermission so you can get up and stretch your legs, but come back because we actually put something together for you that you might be interested in. Take a look.
This is really cool. We have built these trees. We even have our TreeStuff crane, and we're using this to do rigging demos in a way that we can show it multiple ways. So Mark needs no introduction, but Mark's going to show us 2 ways of cutting this limb. One using some conventional I&I type kind of flat slings. You have to use your imagination. And then another way, and I won't spoil the surprise, but go ahead, dive right in, Mark.
All right, so most times when we talk about crane work, the traditional method would be to use some type of fixed length slings. Usually 2 are the most common, and it works for a lot of stuff. For example, vertical picks, when you're just picking something that's straight up and down, it's the simplest, easiest way to go for sure. But a lot of the trees that some of us have to deal with are really awkward in shape, and that becomes more challenging. And the reason it's really challenging, because if it's growing at an angle, say like this, and you have two fixed length slings, a lot of times people aren't making a mistake of where they put the crane hook. That's not the problem that causes a lot of movement or shock loading. What the problem is the approach using the rigging and also pairing it with the wrong cut. So simple way to look at it is you're going to use one sling on each end of this leader, if you will, hook it back to the crane, and as soon as we do this, you're going to notice a little bit of a problem. We're going to try to balance it out to where they're equal in distance from center point, so the angle is right, and you notice it doesn't meet back. So a lot of times we have to pull that crane back down. If you can cable down a little bit. All right, now pull that back up and look what we have. We have one tight and one not tight. So what does the climber tend to do? Well, they say, all right, I'm going to fix this. And they say, give me some more slack again. Cable down. Take the sling off. And mind you, you're working with big slings and difficult work positioning. This doesn't happen very quick.
And the hook also has to come down to you each time.
It does.
That was always
around,
a big thing for me.
And then you have to try to visualize, what do I need to do to adjust for that? So a lot of times people will say, oh, I'll take an extra wrap. And sometimes that works great, but a lot of times it's not perfect. So now we rehook it, and then we have to do something where you pull it back up, and maybe it's a little off balance or it's really well done, depending on the scenario. If you have a different growth pattern, this changes things, you know, because now your angles are different. So in some ways, it could be dangerous to the climber. In other ways, it's dangerous to the structure. So when we make this cut, it tends to be not quite balanced. It's going to move one way or the other. You know, and that's the issue we come up with. So if it's upwards like this and we have slack in the top sling, this is obviously going to jump up a little bit, and that's maybe problematic for the climber, and the tip may dive, and vice versa in the other direction. So let's go ahead and make the cut, and I'll show you what I mean. This shouldn't move too much because we really don't have a lot of end weight, but the concept is really the same. All right, stand clear. I'm not going to hold it because I don't want it to move too much or limit the movement. As it comes off, you see it moves around a bit. Now, granted, this is a really controlled environment. In the real world, this thing could weigh 5,000 pounds or more because you're doing crane work. So as this piece moves just this much, pops up and down near the climber, it could go in either direction.
Right, and if I had weight here, I mean, we can see that it definitely would be tipping.
Absolutely, and you also could have side load here or there, and that's going to cause it to twist too. And when you get a dip and then a twist and then a turn, it's going to wobble as well. So that butt tends to move around a lot, and at times what usually happens is the crane operator is going to be worried about the climber, so they're going to try to make they're going to see this being off center, and they're going to make some adjustments too. So when you do cut it, you know it's going to move a lot because the crane operator is trying to protect the climber, and that's always, you know, a good thing. But again, it's something that you're trying to limit. I like to try to limit movement as much as possible, you know, and that's where a lot of my rigging starts to really stem from. When you get out in the real world and you see a scenario where it's difficult, it's not just the time waste where the crane has to come down, take the sling off, put the sling back on, then you wrap it, then it's not right, then you wrap it again in a different way and it's still not quite right, and then you say, okay, well, it's close enough. And close enough might be good, but close enough can also be dangerous. So one way I found to deal with it years ago is using just a different type of sling. And at first, it seems like it's going to be more involved, more time-consuming and all that. But when you use it as a system for 1 cut, 2 cuts, 3 cuts throughout the process, you realize not only is it safer and easier, it ends up being a time saver over the long haul. So now let's go ahead and get that up in the air a little bit again. There you go, perfect. Now, when we use slings that are dead-eye slings, they're not fixed length. They can even be different lengths, and that's one of the beauties of it, because for example, here we got 2 different colors. One color could indicate that one is longer than the other, which means you're going to put it in the furthest point you need to rig to. In this scenario here, we can do the same thing. We can do 2 cuts, or rather 2 slings, and it's very easy to try to set this up. So we come out here to the same spot as before, use an approved hitch like a cow hitch, for example, and we're going to rig this piece back up. And what you're doing is you're going to try to get it tense, the sling just tense enough to where it's not coming, where it's going to be real slack, but you're not pulling the hook off center. And then we anchor it with, like, say, a half hitch on top so it can't move, or 2 or 3, depending on what you're doing. So now we're going to do the same thing. We don't need to incorporate a 3rd sling, but you could if you have some awkward shape. But here you can see they're both a similar angle, One's longer than the other, and it doesn't take any adjustment. You don't have to bring the hook up and down,
Right.
wrap it, check it again, do it again. It's one time, and it's so
And had
simple.
that other sling not been like essentially perfectly double the length it needed to be, you would have had it wouldn't have
Worst
matched up as
scenario.
well as it did in
Absolutely,
our first
because
scenario.
in the real world, branches don't always grow so symmetrical, right? So
Right.
you're just going to have to fight some weird shapes and some long limbs and some side load as well. You know, and this can actually do that. So if you have side load here, you could just do something like this. And this is just a balancer. It's not for strength, really. It's just to keep that from torquing around. So if that's a long extending limb, now you're controlling the center of gravity of the branch, and that's what your goal is. So you put the hook right where you need it. You don't move it again. You put your slings tight, then you make your cut, and then again you have the same deal. So now you got, thank you.
So we've added a little weight out there now.
And that's going to make it a little more wanting to twist off. Sometimes what you're worried about is a certain angle of movement or a certain direction of pull one way or the other based on the slings and the weight. So for example, if this house is very close to here, you may not want to have this butt chance going downward because this is fragile stuff. You don't want to break something. So what I would do here is I would make a flat cut horizontal to the ground to make that cut. Doesn't matter where you start it. It's not a pruning cut, so it can be as awkward looking as possible. It doesn't really matter. So what I'll do is I'll make a flat cut horizontal to the ground, and I'll just bring this in as far as I need to get enough of a shelf underneath that piece to hold it in place. So you bring it in as far as you need to have some stability. Now, if this crane is a little bit slack like it is and it does dip, it won't go down because there's a shelf. And we didn't have to use a butt rope. We didn't have to do anything really complex. It's just making a cut different. Then you make your top cut, and how you make it doesn't matter. It can be any angle as long as there's no fiber left. So you can make it further out. You can make it on another angle. You could protect yourself and put in an angular cut here if you're cutting from here.
Oh, I really like that.
So that way it protects you. Oh, this is where it kind of came from before. It's like a cut like this, and you have to be positioned here. I can make a step cut this way. The goal is to make sure your cuts bisect or intersect, and they don't leave anything slack. So I don't want to make an angle like this, and then there's fiber to cut. So I'm going to try to make sure that before I start my cut, I feel where that kerf is, and then I'm going to dial it in. So now I'm going to make a cut that kind of is straight down. And as I'm coming through it, when you do crane work, you're watching the kerf to see what's going on. If my saw starts to get pinched this way, I know movement's happening. And then I can readjust my body position or readjust the crane. So here I'm just going to make this cut. And as you can see, it's slacking a little bit because we don't have a lot of tension. And eventually, this is going to come off the cut. And it doesn't drop because you got that
it's disconnected
shelf.
now.
Yeah.
That's what you're telling me.
Yeah. So as it's swinging around, you can see it's just kind of sitting on this ledge. And this is not just here because it's a model. Actually, it works great in the real world, and that's kind of why it's an interesting way to do it for me.
So if I cable up, is it going to stay balanced?
It should be pretty balanced. I mean, I'm
so?
not the best at balancing, dry wood like this with no leaves on it, but it's a learning
All right, let's
experience.
watch.
But go ahead.
Cable up. Can you show me the signal?
Yeah.
Fast or slow?
We're just going to go normal. Wow, Nick, you're a great crane operator. Now, hey, can you swing left?
Yeah,
Can you
no
swing
problem.
Left? Get it away from the climber in the house,
Sure,
please.
no problem.
Swing left.
Mark, I think that what you just showed us was full of really great tips that I think people can take away and use to make themselves safer. Mark, thank you so much.
My pleasure, man.
I
Thanks for
loved
having
it.
Hey guys, thank you very much for sticking around. Gave me a chance to drink some water. My voice was getting pretty hoarse there. So anyways, I left you with contact is contact, right? So, we talked about direct contact and indirect contact, and direct contact can also be involved with the service drop or the triplex that's going from the transformer at the pole to the house. And a lot of people think that these things are insulated because they got black coating on them, and that is simply not true. Service drops, they are common, 120 to 200 amps, and think about this. So maybe I've done it. You guys have installed an electrical outlet or a switch inside your home, and you failed to turn the breaker off and you shocked yourself, or maybe you arced and sparked a pair of pliers. Don't think that just because that was a little spark or you felt it and were fine that you would survive out on a higher distribution line, because remember, when we go back to the amps, ohms, and volts theory, so your service inside of your home is protected by breakers that are rated for a certain amperage at a lower, much lower voltage than distribution or transmission voltage is. So just because these things you think are insulated, they're not, and they do have absolutely enough amperage flowing through them to kill you. Because remember, it only takes 1/10 of an amp, right? And a lot of times these things are old. The weather heads are old, the crimp connections at the pole are old, or the service drops have been routed through trees. When they're routed through trees, trees will, kind of absorb them, go around them, or they'll rub as the wind blows trees around. And these things can absolutely become, either loose or just corroded over time and basically fall apart with just a simple touch. Or if you happen to be climbing or working nearby and you bump them with your pole pruner or your pole saw, just a simple tooth of your pole saw can absolutely cut through the coating on these lines and provide an arc or a spark. So we're going to move on to touch and step potential. So we know that overhead underground or overhead distribution is not safe. We know that underground distribution is not safe, and we've talked about direct and indirect contact. So direct and indirect contact, both involve touch and power lines somehow. And there's a couple other things that you need to be aware of, and that is touch and step potential. So like ripples in water, right? The electricity radiates from the energy source dissipating over distance. So in the center of the ripples on your screen, that's where we kind of tossed a rock and it created ripples, and the ripples radiate away. And the bigger the ripples or the bigger waves are closer to the source, and they get smaller as they get further away from the source. And during touch or step potential situations, it acts very much the same way. On a picture given to us by BC Hydro, this is a picture of step potential. So what we see is we see a caribou and a gentleman in this photo, and radiant rings that are oscillating away from the down energized line in the center. The radiant rings, because they're dissipating, it's not consistent, they're dissipating. So each ring is a difference in potential. So as you're walking or running or stepping or crawling or what have you, as you're traveling, you are stepping in multiple different radiant rings with the difference in potential. And when you cross into from one ring to another ring, that difference in potential is what's going to flow through you and kill you. And then on the next slide here, we have a gentleman with a guardrail. So in this picture, this is another representation of touch potential. So during storm situations, or if a power line happens to fall down and touches a metallic or conductive object, that power again is going to radiate through that conductive object to you, and then you're going to provide it a perfect path to ground. So this is considered touch potential, and this is absolutely kills people every year, unfortunately. And another depiction of step potential. So again, just like ripples in the water, right? As you get further away, the power dissipates, and walking near or working in the area, it would be very, very hard to avoid stepping within the same level of potential the entire time. So you just want to make sure that you're not actually going to electrocute yourself, right? So what do you do? What do you do if you think step potential or touch potential exists? And what you need to do is you need to pull a Michael Jackson move. It used to be said that if you thought you were in an area with step potential, that you would keep your feet together and you would hop forward, hop away from the energy source. The problem with that is a lot of tree climbers and linemen out there have bad knees, and you'd begin hopping and then you would lose your balance, or a knee would give out and you'd fall down and contact the line, or contact the ground and become part of the circuit and unfortunately electrocuted. So the safest thing to do is to keep your feet together and shuffle your feet backwards away from the energy source. So never picking up your feet and never setting your feet back down. Just keeping your feet, both feet firmly planted on the ground, and shuffling your feet backwards away from the energy source is the safest option if you, if step potential exists. If a crew member inadvertently contacts energized electrical lines through either direct or indirect contact, one of the biggest things is you don't want to become the second victim. So if you're not familiar with the situation, if you're not familiar with the voltages or what's going on, it would be very, very hard for you to successfully rescue that person. So the best thing that you can do is to secure the scene to make sure someone else doesn't become a victim. Keep personnel and civilians safe. And if you're working in a city area, civilians may see an injury happening or something going on and want to come investigate or help. And the best thing to do is to keep them out of the area. Notify EMS, the emergency medical services. Notify them, get them en route. Notify the utility company, see if they can isolate the area or shut the power off where you guys are working, and follow any company procedures that you guys have. And something that's not said here on the slide, but you should absolutely know where you're working. So that way you can have it right on your job briefing. You call EMS and you call the power company. You can give them your address and they can come straight to you immediately. So make sure that it's written, it's accurate, and it's legible. So that way anyone on the crew can find it and notify somebody. So we've talked about people and electricity. Let's not forget about our equipment, right? So, I'll just read this out aloud. All equipment and aerial lifts must also maintain minimum approach distance. So if you're a non-qualified person, you must maintain at least 10 feet away from any energized power line or equipment, right? So even if you have an insulated boom, but you're a non-qualified person, you cannot fly that boom closer than 10 feet at a minimum to any energized conductor. If you are qualified, your equipment must be annually inspected and designed for such use around power lines. So maybe you are qualified and you have a boom. That boom truck has to be insulated and it has to be high pot tested annually. And we have an example of what high pot testing looks like. So much like Nick's presentation earlier on the hard hats and them doing the probe test to see if the hard hat meets dielectric testing, buckets have to undergo the same testing annually. So if you are a private arborist and you have access to a bucket truck, just remember that your bucket truck may not be electrically or dielectrically safe. And we have some examples of what bad buckets look like. So if you are a line clearance tree trimmer, or if you have a bucket truck and the steps on that bucket look like this one here in this image, or the boom looks like this and they're all cut up from the stick saw or the Ackley, this thing is probably not dielectrically safe and would probably not pass the test. So just make sure that these items are taken out of service and repaired as fast as possible and not used around energized conductors. So that's the bucket trucks, and cranes are becoming much more popular in arboriculture. A lot of guys have knuckle boom cranes, or they're using crane services, or they have purchased their own cranes. And cranes have a very, very special section as far as OSHA and ANSI is concerned. So in OSHA 1910-26 on page 522, in order for a crane to be used, power lines must be de-energized by the utility operator and visibly grounded at the job site. So we talked about grounds earlier, the hot wire gauge cables hanging from the energized phases, de-energized phases to the neutral, and then to some type of grounding or bonding. Or there needs to be a minimum of 20 foot of clearance must be maintained between the crane boom, the load line, ball, and all other equipment. So that's not only that's clearance vertical and horizontal. Or the third option, as a qualified person can determine the nominal voltage, and using a qualified crane operator can operate the crane and equipment up to the minimum approach distance that person or equipment is actually qualified for. However, if the arborist is non-qualified persons under OSHA 1910-269, the arborist must still maintain a minimum of 10 feet from all energized equipment. So an example again of what that what that 20 feet looks like for the equipment, you know, horizontal and vertical clearance. So absolutely at a minimum is 20 feet. And if we're using the minimum approach distance charts, as that voltage increases, the minimum approach distance also increases. So, you know, we've kind of talked about basic electrical hazards, basic electrical awareness of apparatuses and equipment that you'd find on poles, overhead, and underground. Now let's look at a couple more advanced things. So the image that you see on your computer, or images, is of storm situations, and that picture with the snow is actually one I was on in Washington. And you know, typically when trees are intertwined with power lines, you're going to have a lot of tension and compression in all kinds of different directions, and they require special tools and special techniques, special knowledge and experience to do safely. So we're going to watch a little video. I know that some of you guys have probably seen this. It's been around recently, but let's watch this video and see what happens when you don't control the situation.
Holy shit.
So we've watched the video now, and unfortunately, you know, that gentleman is alive and he's all right, just so you all know. But just the beginning of that video, watching it, you can tell right away that something's wrong. He's definitely in the bite. He's working on the wrong side of that tree. The tree's not tied down, and the power lines aren't tied down. So whether it's be a power line or some other version of a line that is under tension, or if you maybe are was asked by your utility or a homeowner to come out and remove a tree off of their service drop or what have you, if there is a line under tension, you need to employ some serious techniques to make sure that that line does not come springing back up and thrust that tree in any unsafe direction. So we're going to give a little example of some techniques that we use out here in the Northwest as line clearance tree trimmers. So we have a tree that's landed on a power line, and it's got it pinned down pretty tight. And fortunately, in this example, is we have a stump as well. So we're going to call that stump an anchor. It's an available anchor. And on the next slide here, what we've done is we've just simply tossed a rope up over that de-energized, isolated, grounded line and secured it to the stump. So now what we can do is we're safe to work that tree off without fear of that line coming back up into the air uncontrolled. And if we need to gain extra tension on that line, we can employ just simply a set of 4-ways and a prusik or VT on that rope and have the force enter that anchored to that stump, and then we can apply a lot more pulling power on that line and get it really under control. So, you know, those were pictures of if the stump was available, right? So now what if no stump or no available anchor is available? And this is a technique that is absolutely a game changer for a lot of people in the Northwest. So again, we're in the middle of the span, and we don't have an available anchor to use. So we're going to tie a rope, and here we have a green rope that's going from the left to the right, and it's secured at both poles, you know, or it could be a pole and a truck or what have you. In the center, we're going to tie an alpine, butterfly, or some type of midline knot, and we're going to secure a porta wrap or another friction device, portable friction device, on that midline knot. And then we'll go ahead and take a rope from there and secure it over the wire or over the item that we want to control. And then we can use the set of 4s and really gain a lot of pull and tension on that line. And then we'll secure it and cleat it off with a set of 4s, or excuse me, on the porta wrap. And then once it's secured, then we can turn our attention back to the tree. So now we have a tree, and what we want to do is we want to reduce that tree to its simplest form. So we know that we're gonna remove all the hair off of it, all the foliage and branches. We're gonna cut all of the stubs flush. to make sure that that tree isn't going to get caught on that line any longer, and we have absolute control over it. So, you know, again, this is a very simplified picture, so we don't want to, you know, there's special cuts involved. There might be more ropes or another porta wrap involved in doing this safely, but in its simplest form, you just want to at least reduce the tree to its simplest form, and then once the tree is on the ground, and then you're able to safely and controlled release the porta wrap, letting the lines retension back up into the air. So again, this technique takes some practice, but it is a very, very valuable tool to have in your tool bag. And just for some clarification here, on OSHA 1910-269, during storm work, line clearance tree trimming may not be performed when adverse weather conditions make the work hazardous in spite of the work practices required by this section. Each employee performing line clearance tree trimming in the aftermath of a storm or under similar emergency conditions shall be trained in the special hazards related to this type of work. Now, anybody that's been around for a few years has probably seen some unimaginable things during storm work, and it's almost impossible to be prepared for all of them. The technique we just looked at is one technique. It's not all-inclusive, and you know, if you're going to be working out on storm as a line clearance tree trimmer or a general arborist, just please make sure that you are trained in the storm response. So how can you stay safe whether you're in storm or you're doing just traditional work? You need to educate yourself and be aware, know the voltage and maintain minimum approach distances. You can contact the utility and wait for grounds in the event of storm work or if something was to become damaged. Use proper personal protective equipment. Maintain dielectric equipment. If you actually have dielectrically tested equipment, maintain it. Stay away from down power lines and all electrical equipment. Okay. So we're going to educate ourselves and know our limits. So know your personal limits too. You know, be okay with saying I don't know or I cannot do this. Be a team player, and again, be your brother's keeper. Always be aware of your surroundings. So above you, to the side of you, you know where your teammates are at. Knowing the voltage is very important, and there's some simple ways to kind of tell the voltage here. You can contact your local utility. You can observe signs and other postings, pole structures, and telephone poles or high voltage transmission lines might tell you and inform you what voltage is. You can identify the height or the height of the pole structure and observe the number and the size of the insulators. Usually the primary is at the top of the pole while the neutral and communication lines are below. And of course, the higher the voltage, the larger the structure, pole, and attached insulators. So if you see something with very, very large insulators or a multitude of insulators, you can take a safe bet that the voltage is quite high. But if you want to know actually what it is, for sure, contact the utility and give them a location of where you're working, and they can tell you what the voltage is. Grounds and clearances, we talked about it earlier in the definitions. We looked at alignment, installing grounds on the line, and we're going to talk a little bit more about those and what they do for line clearance tree trimmers that are out there working on the wire. So working grounds or field grounds, personal grounds, they have quite a few different names. All equate to grounds that are installed at the immediate working area. So these are grounds that you can actually visually, tangibly see in your immediate work area. The lineman tests the power line to ensure there's no current or voltage running through the lines, and then they install their working grounds. As mentioned before, the grounds provide the shortest path for fault current into the ground and aid in the tripping of a circuit protection device. So let's look at a little diagram of kind of what that looks like here. So we've got some power lines moving from left to right, and we got a tree in the center and a substation up in the upper right-hand corner, and electricity is moving right to left, right? So let's take a look here on this next slide. Okay, so we've got again a substation up there in the upper right-hand corner, and power is flowing from right to left, and we got a tree right in the center. And let's say that this tree kind of falls over and tears down the wire. And let's see this animation play through here. So we've got the tree laying in the middle of the power lines, and the lines are sitting there on the ground, right? Why don't we go ahead to the last animation on this slide? Okay, very good. So the tree's fallen through the power lines, and the lines are left laying there on the ground. And what this can create is a phase to ground fault, like we talked about earlier, and we have a little gentleman who walked up there and got electrocuted. It can also create a backfeed situation, which we discussed earlier as well. So, you know, the customers down there at pole 1 all the way up to the end of the line, they want to install the generator. And that generator, if it's installed improperly or not disconnected from the system, can backfeed towards where the down wires are at and cause a potential injury or death. So what do? We got to get grounds installed, right? Or create an EPZ zone. So on the next slide, we're going to take a look at what that actually looks like and how the area is isolated. So we'll run through this animation here, and then we'll point out all the different objects that the animation shows. So in this area, we have the cutouts at pole 2 are open, and what that does is it isolates any potential backfeed. There's grounds that have been installed at pole 3. At pole 4, there's also grounds installed, and then at pole 5, a switch has been opened. So a switch, kind of picture it maybe like your light switch or a smaller breaker version. It's used to isolate sections of line. In this context, in this narrative, it's used to isolate sections of the line downstream. So in between spans 3 and 4 where the tree has fallen, we're protected by grounds on both sides, and we know that the area is isolated. In this context, it's isolated by open cutouts and an open switch. So the area has been isolated, grounds have been installed, and now it's okay for the tree guys to go ahead and go in and do their work. Now, don't get confused. This is not tree guys installing grounds, right? This installing grounds and testing for voltage. This is all done by the utility linemen or their subcontractors. So the safest thing to do in storm situations or where a tree has contacted power lines is to wait for the utility to come and to make the area safe, right? So other than that, we can look at some other things that are within your control, and that's going to be PPE. And we see some pretty funny examples of what people think PPE is. We got a hard hat with some holes in it. Obviously, that's not going to pass dielectric testing. A gentleman who definitely, is doing some grinding and is protecting his eyes with a plastic bag, and another gentleman who doesn't want to fall off the roof installing some Christmas lights. These are all failures of what PPE is. So let's show you what some wins are for personal protective equipment while you're working around power lines. So in this next slide, we have a Buckingham Buck-Ohm harness. Now, where the potential for an electrical hazard exists, your fall arrest harness must also meet other requirements in addition to subpart M requirements. So subpart M is the fall arrest standard for OSHA, but in addition to those standards already listed, if you are working around an electrical hazard or the potential for electrical hazard, you need to make sure that your harness can successfully pass a drop test after exposure to a 40 plus or minus 5 calorie per centimeter squared electrical arc. Now, I know that sounds like a lot, but to put that into perspective here is 1 calorie can be described as holding a big lighter 1 inch away from your finger and holding it there for 1 second. So the amount of heat that you experience in that 1 second from that one big lighter is about 1 calorie. So between 35 and 45 calories per centimeter squared, that harness has to handle a successful fall after being exposed to that electrical arc. And what that is kind of representing is that you're up in the bucket and experience an electrical arc, and you're kind of blowing out of the bucket, and you've suffered that heat and then have also fallen. So they want to make sure that that harness is going to hold up. And then also, those harnesses are dielectrically tested. So it can have no visible deterioration after a dielectric test of 25,000 volts per foot for 3 minutes. And if you'd like to find this information, it's on page 405 of the OSHA 1926 book. And hard hats. So I know I mentioned Class E hard hats earlier, and there are other hard hats that are Class E that are, you know, non-traditional. So like we have the Petzl Vertex Best here, which I actually own one, and that is a Class E rated hard hat or helmet. In the middle is a Fanner Protos, which I also have one of those, absolutely my favorite, but it's not Class E rated, and we cannot use that around where energized power lines or the potential for energized conductors are. And on the right is a classic wide brim hard hat. Just make sure that if you are going to work around energized power lines, that you need to inspect your hard hat and make sure that it has a Class E, ANSI Class E rating on it. And what that means is it offers dielectric protection up to 20,000 volts. And that 20,000 volts is measured phase to ground. Something else you guys must be aware of, that whether it's a Sherrill Tree catalog or Westberg catalog or what have you, if you are using Jameson poles or any other type of pole hook and you think that tool is insulated, be aware that there are electrical hazard warnings everywhere. These tools, if they're marketed as dielectric, then they were dielectrically tested at the factory, but then they've been sent out to you. They have not undergone annual dielectric tested. You guys are probably not, you know, or maybe you are, but there's potential that you are not maintaining them with wax wipes. They could be cracked or broken or dirty or wet or what have you. So just make sure that you, when you purchase something, if it says that it's dielectrically tested and safe around a certain voltage, it also has to be maintained and used a certain way in order for that to actually ring true. Something else you guys need to absolutely do is have an AED present if possible, if your employer can provide one. You know, it takes 1/10 of an amp to send your heart into cardiac rest or give yourself an irregular heart rhythm. Having an AED at the job site or available maybe in the GF's truck, the owner's truck, could save a life. Also having your first aid supply stocked and easily accessible. And there is some language talking about first aid. So OSHA 1926, when employees are performing work or associated with exposed lines or equipment energized at 50 volts or more, persons with first aid training shall be available. Now, that's not the whole quote, but it's on page 404 if you want to read it, and 1926. And in the ANSI Z133, the employer shall provide and maintain a first aid kit that meets the requirements of ANSI Z308.1 with contents appropriate for the type of job and number of workers. So if you are working around energized power lines, then there's going to be some specific requirements that your first aid kit is supposed to have. And getting back to the job briefing a little bit and what you can do to keep yourself safe and your team members safe is knowing your location, doing a great job briefing, and knowing what medical facilities are around, because not all medical facilities are actually equipped to deal with electrocutions or severe burns. So already being aware of where you're at, it might change your work practices a little bit, or once you call dispatch, you already know the information that you need to give them, the nature of the injury, what happened, the extent of the injury, and where that person needs to go. So know your location, have a medical emergency plan, have a cell phone or radio reception, clearly explain the nature of the industry, giving as much detail as possible to dispatch. That's going to help prolong someone's life, right? So let's recap some OSHA stuff. So the OSHA governing standards that we talked about were 1910, 269 subpart R, 1926.96 subpart C, and ANSI Z133, the 2017 edition. and in general industry, 1926. So subpart B of power transmission and distribution. So if you want to learn about special rules that have to do with power transmission and distribution, remember that it's in subpart B as in Victor. Line clearance tree trimming performed for the purpose of clearing space around electric power lines or equipment and on behalf of an organization that operates or that controls the operating procedures for those lines or equipment shall comply with 1910.269 of this chapter, which is what we've been discussing. Training qualified employees. So the skills and techniques necessary to determine the nominal voltage of exposed lead line parts. So the qualified employees must have training and the skills on this next slide here. You can read it along with me. The skills and techniques necessary to determine the nominal voltage of exposed live parts. Can we, let's see here, can we skip slides? Let's see. Oh, there we are. Okay, and the minimum approach distances specified in this subpart corresponding to the voltages to which the qualified employee will be exposed, and the skills and techniques necessary to maintain those distances. They must also be trained in the recognition of electrical hazards to which the employee may be exposed and the skills and techniques necessary to control or avoid these hazards. So what does that mean, right? All employees deemed qualified must be able to recognize the electrical hazards, know how far to stay away from the hazard, and have the tools and techniques to do so. Okay, so let's do a review together of what we talked about today. So we've talked about some definitions, what makes a qualified person. We've talked about amps, ohms, and volts, hardware and apparatus identification. We've looked at the MAD chart. We know that there's two different MAD charts, one for qualified, one for non-qualified. We've looked at overhead and underground construction, service drops, touch and step potential, equipment installation and high pot testing, lines under tension and kind of how to go about it, or one technique to go about it, clearances and grounding, and some personal protective equipment. So before we move on, before I give this back to Jake here, I do want to provide an option for any questions from anybody or to answer anything that I might be able to answer. So do we have anything?
All right, Keith, Gary Thacker is asking, how does OSHA recognize incidental line clearance arborists working within MAD?
Gary, so how does OSHA talk about incidental line clearance and working within MAD? So this is definitely a hot topic, and my best advice to that would be to contact your local office and get a direct definition from them on how they recognize that or how they want to go and approach that. In my current position, I necessarily can't speak of that because I don't work for OSHA. And I don't want to give you misleading information.
Okay.
Good question, though.
Yep. Nels Backstrom says he's sorry if it's been covered, but is 10 feet from house drops correct?
10 feet from house drops, correct or not correct? So on the qualified person's house drops, we're talking about 120, 200 amps. That would be an avoid contact. For somebody that is non-qualified, it would be considered 10 feet according to OSHA. It would be 10 feet.
Okay. John Cole is asking, I've always been curious about this. What would happen to a throw line if it contacted power lines phase to phase? Would it burn up relatively quick? Does the smaller diameter conduct just the same?
If it's conductive, it can conduct. So would it conduct just the same? No, it would not conduct just the same. It probably would not conduct long enough for a circuit protection device to see it. It would probably, this is speaking probably. I personally haven't done this test, but it would probably burn up awfully fast, and that would be the end of it.
Mm-hmm. All right, Frederick Goddard has a question. On the ISA utility specialist test he took, one question that sticks out in his mind is, if the line comes down and the scene is secure, who is your first contact? A, the fire department, B, the utility. Not sure of the other two answers, he was saying. He was trained to contact dispatch through the utility, and they can get the proper resources. In the training manual, it doesn't say one before the other.
In my experience, I would absolutely say that contact the utility or dispatch is absolutely correct. You know, maybe a emergency medical service gets there on site, but they don't actually know any type of hazards or what to do, how to stay away from it, maybe how to put the fire out, whether it's an electrical fire or a chemical fire, or it's, you know, there might be some type of PCB in the transformer. Contacting the utility first would absolutely be the number one, and their dispatch system, I can guarantee you, no matter where you're at in the country, has the resources available to get, whether it's, you know, the CDC or the fire department, the CDC. I don't know why I said the CDC, but whoever is needed on site, they absolutely have the power and the contacts and the phone number to get who needs to be there and as fast as possible.
Okay. Paul Allen is asking, considering the step potential ripples, it would really be good practice to stay clear of the grounds installed during storm work. Is that correct?
So there's some yes and no to that. It depends on how the grounds are installed, on whether they're actually bonded and there's actually ground stakes in the ground. So if there is, if there is grounding to a bracket ground on the pole, or if there's a grounding rod where the things are actually bonded to, then absolutely there is step potential around that rod or around that pole ground. If grounds have been installed, there's absolutely potential for step potential. Now, it being in the ground, that grounding rod, it's going to provide an excellent ground. So, you know, in most cases, right, the person walking nearby is going to be less or not as good of a ground as what's been provided. So, you know, it should be safe, but there is absolutely potential for step potential.
And then he's got a follow-up question as well. In the case of accidental energizing, the installed ground could themselves create the same step ripple. Is that correct? Because the guardrail shown was itself grounded.
Can you repeat that last part again?
Because the guardrail shown in the graphic, that itself was grounded.
So let's think about this here. So if there was a fault or backfeed happened and grounds were installed, the question is, would there still be step potential? Am I understanding that properly?
Yeah, I'll read it again. So
okay.
In the case of accidental energizing, the installed grounds could themselves create the same step ripples. Is that correct? Because the guardrail shown was itself grounded.
If I'm understanding the question correctly, I'm going to say yes. Those grounds are there to basically absorb that fault current or that, you know, inadvertent current that's coming. It's going to provide it a shortest path to ground. So it depends on whether it's, you know, bracket grounding or EPZ grounding. There's several other types of grounding out there. And it depends on where you're at and the pole construction and the utility company on what kind of grounding is going on. So I would say moving forward, it would be safe to assume that there is absolutely the potential for a step potential situation if electricity was inadvertently backfed or a fault current was to exist into grounds.
Okay. And then going back to when you were talking about the porter wraps, would you use a porter wrap to release the tension?
I would absolutely use the porter wrap to release the tension, yes. So after I've, most of the time I'll put a set of fours on it to get as much tension as I can, and then I'll fill the barrel up on the porter wrap and cleat it off, remove the tree, and then once the tree's gone and the wire is ready to be released, I'd uncleat it and then let it go back up, because there can be an absolutely immense pressure on those power lines when they're pinned to the ground or what have you, and releasing it nice and slow and controlled with the porter wrap is by far the best option, because then you're not going to allow that power line or whatever cable to go up into the air and maybe hit somebody that's up there in a bucket, or go up there flying and break itself up off the pole, or contact another phase wire. So yes, absolutely, Porter wrap to release the tension wire.
Okay, and then here's our last question. He was basically wanting to go back to storm restoration for utility line clearance arborist. The 16-hour shift, is that OSHA standards or Department of Transportation laws? Both or neither? I know at times of need, we may or may not be needed for a duration of longer than 16 hours.
So I'm not really quite sure whether the Department of Transportation came in on that. Is that correct, Department of Transportation? Did I hear that correct there, Carson? Okay. I'm not sure where the Department of Transportation comes in, unless you're talking about CDL vehicles and how much brakes need to be in between operating, or whether or not you have to have a certain amount of time of hours off. That's the only Department of Transportation caveat I can think about. Other than that, I tell you, I've been all over this country, and in storm situations, there are utilities that could work upwards of 42 hours straight before you are relieved. You know, when storm or emergency conditions exist, there's all kinds of different things that go on, and I don't know if there's an OSHA stipulation on what is allowed or what is mandated or not mandated. But I can tell you that it's different. I've experienced it different all over the country.
All right, Keith, thank you so much. Very interesting and important presentation. Now, we want to give you a heads up on what's coming up. In the next 2 weeks, on the 22nd of August, we have Albert Cooper, who will join us on the TreeStuff webinar train with a look at how to take care of trees in hot weather. I know many parts of the country are going through hot weather phases, so how exactly do you want to take care of trees in hot weather? Well, our plant healthcare expert, Albert Cooper, will give us some insight into that. And we'll have CEUs available for that webinar. That is on the 22nd of August. And next month, our good friend Joe Aiken will be here joining us for an interesting webinar titled Redefining Evergreens. This is something he's been working on for months, and he has got it finished. He's ready to present it. And very interesting topic here that we want to definitely discuss there. That is next month, Redefining Evergreens. And as I mentioned earlier, Jambo 6 wrapped up just a few weeks ago, and I'll tell you, it was amazing. We had, 3 days of competition, then we had a training session on that Monday. We had tons of people show up, and they got CEUs from ISA and from the Tree Care Industry Association, and we thank them for offering those CEUs. Lots of fun. It was great seeing great making new friends, and obviously seeing old ones, and obviously some great climbers strutting their stuff out on the limbs. And we want to take a moment to congratulate Return of the Mac, the all-Canadian team, for winning it all. Mark Gadet was on the team last year that won, and Chris Stratting as well. Well, it was almost a repeat there. So congratulations to those expert climbers. And thanks to everyone who's been a part of this webinar. And thank you for watching. Now, we want to leave you with something very special here, so don't go away yet. We have a look at one of the most popular games at Jambo and the amazing host who cheers everyone on, Jambo Man. We'll see you later.
Are you ready to Jambo, baby? So what's going on here is the Jambo claw game.
Claw game is one of the best parts about Jambo.
We got 4 climbing systems here. There's a zigzag, there's an akimbo, there's a Blake's hitch, and there's a rope runner.
And participants will jump up on the pedestal. Jambo Man affixes you into the human claw climbing system. Climbers then take themselves from the pedestal out into the prize pit.
And there's all these boxes laying around on the ground. You grab that box with your feet.
And then they have to use those same 4 climbing systems to navigate back to get that prize back onto the starting pedestal, just like the claw games that you're used to when you were a kid.
If you drop the box doesn't get on the stump, or you touch the ground, tough luck. It's a mystery grab. You don't know what you're gonna get. Could be really cool, could be not so cool, but it's Jambo, so it's probably really cool. Could be rocks, could be cups, could be a chainsaw, could be a
climbing gear. You open it, see what's inside.
I'll come away with something. I don't think you don't really win this game. You just get some cool stuff.
I won some clippers, rope bag, a banner.
I'll get a box for sure.
Come on, man! Come on, man!
Jambo Man is here the whole time, Robert Albritton cheering everybody on and helping them through it.
Jambo Man, he's got some energy. He's a great guy. This is pretty fun. It's a different experience.
I like, swinging around on ropes and stuff, so I'm kind of excited to try it out.
Now, who's your best friend in the whole wide world? Come on, man!